All right, hello. We are starting section 6.2. Before we jump in with our notes, I want you to put your notes aside for now, and we're going to do a little bit of an exploration. Okay, what we're going to do is we're going to look at what happens when I do a perpendicular bisector of each side. So let's go ahead, let's add some, I'm going to add some text over here. Side, if we do perpendicular bisector of each side. Okay, the perpendicular bisector. Okay, if you remember from last section, perpendicular intersects at 90 degrees. The bisector cuts it in half. So we're going to perpendicularly bisect each of these sides. So I'm going to take A here, and I'm going to draw in the perpendicular bisector. GeoGebra makes that job really easy for us. Is that if I hit this fourth one over, there's an option for perpendicular bisector. And if you notice down here, it actually tells you how to find it. So down here, select 2 points or one segment. So I'm just going to come in and I'm going to select segment A. So what that's done, this new black line here, is now that perpendicular bisector of this side, meaning it goes through this midpoint, and we can always check that by putting a point there and finding that distance. So this distance here is 4.78. This distance here is 4.78. So it's the bisector. And it also goes through, it also intersects at 90 degrees. So we could actually check this angle here and double check and make sure it's 90. Oh, went the wrong way. How many people do that? Do it all the time. Okay. Why isn't it wanting to go the right direction? Okay, and we see there that we're 90 degrees. Okay, so it is in fact the perpendicular bisector. Okay, so we know how to perpendicular bisect a side. Okay, now we're going to put these segments or these sides together to make this triangle. So I'm going to see, well, what happens when I perpendicularly bisect the other sides? So first of all, I'm going to go ahead, I'm going to come in and I'm going to get rid of this stuff. It kind of clutters things up a little bit. We know it's a perpendicular bisector. Let's perpendicularly bisect side B. So let's come in, perpendicular bisector, let's click on B. Oh, there it is. So there we've perpendicularly bisected. And if you notice here, these intersect at this point here in the middle. Let's give that point a name. Call, why isn't the name showing up? Name. Call it point E. Okay, so let's call that point E. So we notice they intersect there at point E. Okay, that's kind of cool. Okay, but what else do we notice? Well, all right, so it intersects here at point E. Okay, and that's bisecting 2 of the sides, but triangles have more than 2 sides. Triangles have 3 sides. So let's go ahead and let's bisect this 3rd side. Okay, before I go ahead and do that, I want to go ahead and I want to ask your opinion. What do you think is going to happen? Okay, do you think it's going to intersect here point E like these other 2 did? Do you think it's going to intersect them somewhere else? Okay, what do you think is going to happen? So go ahead and give that a little thought. All right, let's go ahead and let's put it in and let's see. Oh, it did intersect a point E. So all 3 of these lines intersect, okay, all 3 of the perpendicular bisectors intersect at 1 point. Okay, that's kind of cool. So all 3 of the perpendicular bisectors intersect at 1 point. Okay, and we actually have a special name for if we have 3 or more lines all intersect at 1 point here. We call that, we say that word is concurrent. So we would say they are concurrent. Basically, that just means that 3 or more, we would say they are concurrent. And we'll talk about all this in our notes. Basically, that's just 3 or more lines all intersect at 1 point right here. We say they're concurrent. So if you have 4 or 5 lines all intersecting at 1 point, the word for that is concurrent. So instead of saying, oh, they all intersect at the same place, we would say, hey, they're concurrent. Shortcut way of saying things. Okay. Did I just get lucky and just happen to get the exact right triangle to make this happen? No. Okay. I can move, if I move, oh, cancel. That's wanting me to add text. If I move these points around, if you notice, those perpendicular bisectors move too. but they all still intersect at the same point. And look, that point, we call this the point of concurrency, okay? This we call the point of concurrency. Okay. Can I give it a caption? I thought I could give it a name somehow. But we call this the point of concurrency here. I don't know what caption does. Hey, this is the point of concurrency. It can actually happen outside of the triangle. It doesn't necessarily have to be inside. And it happens outside. If you notice, this is here we have acute triangle, all these nice little acute triangles, but as soon as I make it obtuse, here like this, obtuse angle, that point of concurrency happens outside, okay? And if I was to make it a right triangle, which makes life really neat, if I was to make it a right triangle, that point of concurrency actually is right. If I make this a right angle right here, it might be easier to see the right angle if we put it maybe over here. Okay. That point of concurrency actually is on top of the triangle. It's located there on the hypotenuse. Okay. You want to see something even cooler? Okay, you always be like, yeah, not that cool. Okay. But watch what happens when I find the distance between this point, okay, and each vertice. Okay, this is really neat. So if I find the distance between, let's go between E and A, it's 7.26. What about the distance between E and B? 7.26. What about E to C? Oh, 7.26. It's all the same. So the distance, this straight line distance, if I was to measure this distance, if I draw that segment in, this distance from here to here, okay, and let's not make that segment black. Let's make it pink, just so to keep it. That segment, we're looking at this segment right here and this segment right here, those distances are all the same for any triangle. Look, as I move it, what happens? The distances change, but they're all the same, 6.53, 7.23. I could make a crazy, big, wicked, obtuse triangle, and look what happens. Those distances are still the same. Awesome, huh? Okay, so that's the whole gist of this section, okay, is looking at the perpendicular bisectors, okay, this point of concurrency, and that point of concurrency is the same distance from each vertice of the triangle. Okay, the end.